found your way here tonight. Perhaps the day has been long, or perhaps you're simply the kind of person who finds peace in contemplating the vastness of existence rather than counting backwards from 100. Either way, you're exactly where you need to be. You can let your shoulders drop, your breathing slow, and your mind drift as we explore something truly extraordinary together. Because tonight, we're venturing beyond our planet, beyond our solar system, beyond even our galaxy, to contemplate the entire universe itself.
The cosmos is not just vast, it's incomprehensibly, almost impossibly vast. And yet, within that vastness lie patterns, mysteries, and truths that connect everything from the smallest particle to the largest structure we can observe. Over the next hours, I'll share with you 100 facts about the universe. Some will ground you in what science knows with certainty. Others will carry you to the edges of human understanding, where knowledge blurs into speculation and wonder. You'll hear about birth and death on cosmic scales, about forces we cannot see but know must exist, about light that has traveled for billions of years just to reach our eyes, and about the strange, beautiful mathematics that somehow describes it all. These are not just facts to memorize. They're invitations to marvel, to question, to feel both infinitesimally small and profoundly connected to something larger than ourselves. So settle in, close your eyes if you'd like, and let's begin this journey through the universe together, one fascinating truth at a time. And before we start, if these gentle explorations through science and wonder help you unwind or give you something interesting to dream about, consider liking this video and subscribing to the channel. It helps other curious minds find their way here too, one sleepy wanderer at a time. Now let us begin. The birth of everything. Fact 1. The universe is approximately 13.8 billion years old. That number is so large it almost loses meaning, but try to hold it in your mind for a moment. 13.8 billion years. Modern measurements from multiple sources, including observations of the cosmic microwave background radiation and calculations based on the universe's expansion rate, converge on this remarkable figure. Every atom in your body, every molecule of air you breathe, every photon of light you see, exists within a universe that has been unfolding for nearly 14 billion years. Before this moment, before this vast span of time, there was nothing we can properly describe. No space, no time, no matter, no energy, just an inconceivable singularity, waiting to become everything. Fact 2. The universe began with the Big Bang, though that name is somewhat misleading. There was no explosion in the traditional sense, no expanding ball of fire and debris hurtling through pre-existing space. Instead, space itself came into being. Time itself began. The Big Bang was the moment when everything erupted from a state of infinite density and temperature, smaller than an atom, containing all the matter and energy that would ever exist. In less than a second, in a fraction of time so brief, it defies human comprehension. The universe inflated to astronomical size, cooled from unimaginable heat, and set in motion all the physical processes that would eventually lead to stars, galaxies, planets, and life. Fact 3. In the first trillionth of a trillionth of a trillionth of a second after the Big Bang, the universe underwent cosmic inflation. This period of exponential expansion was so rapid and so extreme that the universe grew by a factor of at least 10 to the 26th power. Imagine taking something the size of a single bacterium and expanding it to the size of the Milky Way galaxy, and you begin to approach the scale of this transformation. Inflation solved several puzzles about the universe's large-scale uniformity and explained why distant regions that could never have been in contact with each other appear so similar. It stretched quantum fluctuations, tiny ripples in the fabric of space-time, to cosmic scales, and those ripples would eventually become the seeds of all structure, every galaxy cluster, every galaxy, every star. Fact 4. For the first 380,000 years after the Big Bang, the universe was opaque. Light could not travel freely through space because matter was so hot and dense that photons constantly scattered off free electrons, creating a kind of cosmic fog. The universe glowed, but that glow could not travel. It was trapped, bouncing endlessly between particles in a plasma so energetic that atoms themselves could not form. Then, as the universe expanded and cooled, a remarkable transition occurred. Electrons combined with protons to form the first neutral atoms, mostly hydrogen and helium. With fewer free electrons to scatter light, the universe suddenly became transparent. The glow we see from this moment is called the cosmic microwave background, and it surrounds us still, a faint whisper of light from the universe's infancy, cooled now to just a few degrees above absolute zero. Fact 5. The first atoms were almost entirely hydrogen and helium. In those earliest moments after the Big Bang, when the universe was still scorchingly hot, nuclear fusion briefly occurred everywhere at once. Protons and neutrons collided and combined, forming the nuclei of light elements. About 75% of the universe's ordinary matter became hydrogen, the simplest element with just one proton. Nearly 25% became helium, with 2 protons and typically 2 neutrons. Trace amounts of lithium and beryllium also formed. Then the universe cooled too much for fusion to continue, and that was it. No carbon, no oxygen, no iron, no heavier elements at all. Those would have to wait. They would be forged much later, in the cores of stars and in the violence of stellar death. But in the beginning, the universe was hydrogen and helium, the building blocks from which everything else would eventually arise. Fact 6. The first stars, called population 3 stars, are thought to have formed between 100 and 200 million years after the Big Bang. These primordial stars would have been very different from the stars we see today. Born from clouds of pure hydrogen and helium with virtually no heavier elements, theoretical models suggest they may have been extraordinarily massive, perhaps hundreds of times more massive than our Sun. Such giants would have burned incredibly hot and bright, living fast and dying young in spectacular supernova explosions. When they exploded, they would have scattered the first heavy elements into space, enriching the gas clouds from which the next generation of stars would form. We have never directly observed a population 3 star, and they remain theoretical constructs based on our understanding of early cosmic chemistry, but astronomers continue searching for them, hoping to catch a glimpse of the universe's first luminous objects. Fact 7. The universe was once much smaller than an atom. This seems impossible, almost absurd, but according to our best models of cosmic inflation and the Big Bang, at the earliest moments, we can meaningfully describe the entire observable universe. Everything we can see in any direction out to nearly 14 billion light-years was compressed into a region far smaller than a proton. Space itself was compacted. Time had barely begun. And yet everything that would become stars and galaxies and planets and people was already there, contained in that inconceivably tiny volume. When inflation occurred, that microscopic seed expanded faster than the speed of light. Not because anything moved through space faster than light, which is impossible, but because space itself was growing, stretching, carrying everything with it. Fact 8. The cosmic microwave background radiation fills the entire universe. No matter which direction you look, if you have the right instruments, you can detect this faint glow of microwave light. It comes from every direction at once, forming a perfect sphere around us, because it represents light that was emitted everywhere in the universe at the same time, 380,000 years after the Big Bang. As the universe has expanded, this light has been stretched along with space, shifting from visible and ultraviolet wavelengths to the microwave portion of the spectrum. Studying tiny temperature variations in this background radiation has revealed extraordinary details about the early universe, from its age and composition to the seeds of structure that would grow into galaxies. It's one of the most important discoveries in all of cosmology, a baby picture of the universe itself. Fact 9. For hundreds of millions of years after the first atoms formed, the universe entered what astronomers call the cosmic dark ages. The cosmic microwave background had faded to invisibility. The first stars had not yet ignited. Space was filled with neutral hydrogen gas, dark and cold, lit only by the dim afterglow of creation. This was a time of waiting, of slow gravitational gathering, as slightly denser regions of gas began pulling in more gas, growing gradually more massive. Eventually, these accumulations would reach the threshold where nuclear fusion could ignite, and the first stars would blaze into being. But for that long, dark interval, the universe was a place of shadows and silence, matter slowly collecting under the patient, relentless pull of gravity. Fact 10. The early universe was extraordinarily uniform, but not perfectly so. The cosmic microwave background shows temperature variations of only about 1 part in 100,000. That's remarkably smooth. If the universe had been completely uniform, however, gravity would have had nothing to work with. Structure would never have formed. There would be no galaxies, no stars, no planets, no us. Fortunately, quantum fluctuations during inflation created tiny irregularities in the density of matter. Some regions were slightly denser, others slightly less so. Over billions of years, gravity amplified these differences. Dense regions attracted more matter, becoming denser still, while less dense regions lost matter to their surroundings. This process, called gravitational instability, transformed nearly uniform gas into the rich cosmic structure we see today. Fact 11. Within just 3 minutes after the Big Bang, the universe had synthesized the nuclei of the lightest elements through a process called Big Bang nucleosynthesis. The conditions were perfect for this brief window of fusion. The universe had cooled enough that nuclei wouldn't immediately be torn apart by collisions, but it was still hot and dense enough for nuclear reactions to occur. Protons and neutrons combined to form deuterium, a heavy form of hydrogen. Deuterium fused into helium-3 and helium-4. Small amounts of lithium-7 also formed. Then, almost as quickly as it began, nucleosynthesis ended. The universe had expanded and cooled too much for fusion to continue. The relative abundances of these light elements, predicted by Big Bang nucleosynthesis and measured in ancient stars and gas clouds, provide one of the strongest confirmations of the Big Bang theory. The universe remembers its fiery youth in the ratios of hydrogen to helium to lithium that persist to this day. Fact 12. The laws of physics, as we understand them, break down at the very beginning. When we try to describe the universe at times earlier than about 10 to the minus 43 seconds after the Big Bang, a time called the Planck time, our theories fail. General relativity and quantum mechanics, the two great pillars of modern physics, cannot both be true in that extreme regime, and we don't yet have a theory that successfully unifies them. We don't know what, if anything, existed before the Big Bang. We don't know if the question even makes sense, since time itself may have begun with the Big Bang. Some physicists propose that our universe emerged from a quantum fluctuation in a pre-existing multiverse. Others suggest a cyclic model where universes expand, contract, and are reborn in an eternal cycle. Still others maintain that asking what came before the Big Bang is like asking what's north of the North Pole, a question without meaning. The honest answer is that we don't know, and may never know, what preceded the moment of creation. The mysterious dark universe. Fact 13. Ordinary matter, the stuff that makes up stars, planets, gas clouds, and everything we can directly observe, constitutes only about 5% of the universe's total energy content. Just 5%. Everything you can see, everything you can touch, every atom in every structure throughout the cosmos is a tiny minority component of reality. This is one of the most humbling discoveries in the history of science. We spent millennia thinking the visible universe was all there was, that matter and energy, as we understood them, were the fundamental constituents of existence. Then, over the course of the 20th century, evidence began accumulating that most of the universe is made of something else entirely. Something that doesn't emit light, doesn't absorb light, doesn't interact with electromagnetic radiation at all. Something dark. Fact 14. Dark matter makes up approximately 27% of the universe. We cannot see dark matter. We cannot touch it. It passes through ordinary matter almost as if it weren't there. And yet we know it must exist because we can observe its gravitational effects. Galaxies rotate too quickly for the visible matter they contain. Galaxy clusters hold together despite not having enough observable mass. The distribution of galaxies on the largest scales follows patterns that only make sense if vast amounts of invisible matter provide the gravitational scaffolding. Dark matter doesn't clump into stars or planets. It forms enormous halos around galaxies and diffuse structures throughout the universe, pulling ordinary matter into the configurations we observe. Without dark matter, galaxies would fly apart. The cosmic web of structure would not exist. The universe, as we know it, would be impossible. Fact 15. We don't know what dark matter is made of. This is not a minor detail to be worked out. It's a profound mystery at the heart of physics. Dark matter is not ordinary matter that happens to be dark. It's something fundamentally different, likely a new type of particle that interacts with ordinary matter only through gravity. Many candidates have been proposed. WIMPs, or weakly interacting massive particles, are perhaps the most popular. Axions, theoretical particles that could solve other problems in physics, are another leading contender. Some physicists suggest primordial black holes formed in the early universe. Others propose modifications to our understanding of gravity itself, though these alternatives struggle to explain all the observations. Experiments around the world are searching for direct detection of dark matter particles, but so far, the mysterious substance remains elusive, known only by the gravitational shadow it casts. Fact 16. Dark energy is even more mysterious than dark matter, and it dominates the universe. Making up about 68% of the total energy content of the cosmos, dark energy is the largest component of reality, and we understand it the least. Unlike dark matter, which pulls things together through gravity, dark energy appears to push things apart. It's a kind of anti-gravity, a repulsive force that permeates all of space. The evidence for dark energy comes from observations showing that the universe's expansion is accelerating. Galaxies are moving away from each other faster and faster over time. This shouldn't happen. If gravity were the only significant force on cosmic scales, something must be counteracting gravity, and that something is what we call dark energy. Fact 17. Dark energy may be the cosmological constant that Einstein introduced and later regretted. In his original formulation of general relativity, Einstein included a term called the cosmological constant, a property of space itself that would create a repulsive gravitational effect. He added it because he believed the universe was static, neither expanding nor contracting, and without this term, his equations predicted collapse. When Edwin Hubble discovered that the universe was indeed expanding, Einstein reportedly called the cosmological constant his greatest blunder. But decades later, when observations revealed that the expansion was accelerating, physicists realized Einstein might have been right all along. If dark energy is the cosmological constant, it means that empty space itself has energy, a baseline quantum activity that creates gentle but persistent outward pressure. The density of this energy would be extremely low, but because it's present everywhere, its cumulative effect is enormous. Fact 18. The universe's composition has changed dramatically over time. In the early universe, radiation dominated. Photons and other particles moving at or near the speed of light carried most of the energy. As the universe expanded and cooled, matter became more important. For several billion years, both ordinary and dark matter governed the universe's evolution, their gravity pulling structure together, forming the first galaxies and galaxy clusters. Then, about 5 billion years ago, dark energy began to dominate. As space continued expanding, the density of matter decreased, spread thinner and thinner across ever larger volumes. But dark energy, if it is indeed a property of space itself, maintains constant density. More space means more dark energy. Now, and for the foreseeable future, dark energy controls the universe's fate, driving an accelerating expansion that may ultimately tear apart everything gravity has built. Fact 19. Some recent preliminary observations suggest dark energy might be weakening, though this remains highly uncertain and debated. If confirmed, It could completely transform our understanding of the universe's future. The standard model of cosmology assumes dark energy is constant, unchanging over time, but certain measurements hint that dark energy might be dynamic, its strength varying as the universe ages. Some data from projects like the Dark Energy Spectroscopic Instrument suggest that the universe's expansion, rather than continuing to accelerate, might actually be beginning to slow down. However, these findings are far from conclusive, and many scientists remain skeptical. If they do prove true, this would require a fundamental revision of cosmological theory. It might mean dark energy isn't Einstein's cosmological constant after all, but something more complex, perhaps a field that evolves over time. The implications would be profound. A weakening dark energy could allow gravity to eventually regain control, perhaps leading to a big crunch, where the universe contracts back to a singularity, or it might level off at some equilibrium state. Scientists are working to confirm or refute these observations, knowing that the answer will shape our understanding of cosmic destiny. Fact 20. The Hubble tension is one of the biggest puzzles in modern cosmology. When astronomers measure how fast the universe is expanding using observations of the cosmic microwave background from the early universe, they get one answer. When they measure the expansion rate using observations of supernovae and other objects in the relatively nearby modern universe, they get a different answer. These two measurements should agree, but they don't. The discrepancy is significant enough that it cannot be easily explained by measurement errors or uncertainties. Something is wrong with our understanding. Either the early universe measurements are flawed in ways we don't appreciate, or the late universe measurements are affected by something we haven't accounted for. Or, most intriguingly, the universe's expansion rate has changed in ways that our current models don't predict. Resolving the Hubble tension may require new physics, new particles, or new forces we haven't yet discovered. Fact 21. Most of the universe's mass exists in vast, web-like structures of dark matter called the cosmic web. On the largest scales, the universe is not uniform. It's organized into a spectacular network of filaments, walls, and enormous voids. Galaxies cluster along the filaments like beads on strings, drawn there by the gravity of underlying dark matter structures. Where filaments intersect, massive galaxy clusters form, the largest gravitationally bound structures in the universe. Between the filaments lie vast voids, regions with very few galaxies, sometimes hundreds of millions of light-years across. This cosmic web traces out the distribution of dark matter, which began clumping shortly after the Big Bang and has been pulling ordinary matter into these patterns ever since. Mapping this web helps cosmologists test their models of structure formation and understand how dark matter behaves. Fact 22. The nature of dark energy might be connected to the vacuum of space. Quantum field theory predicts that even empty space isn't truly empty. It seethes with virtual particles constantly popping into and out of existence, borrowing energy from the vacuum for impossibly brief instants before annihilating and returning it. This quantum foam, as it's sometimes called, should contribute energy to space itself, energy that would behave exactly like dark energy. There's just one problem. When physicists calculate how much energy the vacuum should have, they get a number that's about 10 to the 120 powers too large. This is sometimes called the worst prediction in the history of physics. Something must be cancelling out most of that vacuum energy, leaving behind only the tiny amount we observe as dark energy. What that something is, and why the cancellation is so precise, remains completely unknown. It's one of the deepest mysteries connecting quantum mechanics and cosmology. The cosmic expansion. Fact 23. The universe is expanding, and it has been since the Big Bang. This doesn't mean galaxies are flying through space away from some central point. It means space itself is growing. Imagine dots drawn on the surface of a balloon. As you inflate the balloon, the dots move apart from each other, not because they're moving across the rubber, but because the rubber between them is stretching. Galaxies are like those dots, embedded in the fabric of space-time. As space expands, the distance between galaxies increases. Every galaxy sees every other galaxy moving away, creating the illusion that it's at the center of expansion. But in reality, there is no center. Expansion is happening everywhere, at every point in space, all at once. Fact 24. The expansion of the universe was discovered by Edwin Hubble in 1929. By measuring the distances to galaxies and analyzing the redshift of their light, Hubble found a remarkable relationship. The farther away a galaxy was, the faster it appeared to be receding. This relationship, now called Hubble's law, provided the first clear observational evidence that the universe was not static but expanding. The slope of this relationship, known as the Hubble constant, tells us the current expansion rate. It's one of the most important numbers in all of cosmology, determining the age of the universe, its size, and its ultimate fate. Measuring the Hubble constant with ever greater precision has been a central goal of observational astronomy for nearly a century. Fact 25. The universe expanded faster than the speed of light during inflation and continues to expand faster than light on the largest scales. This seems to violate Einstein's principle that nothing can travel faster than light, but it doesn't. The speed limit applies to motion through space, not to the expansion of space itself. During cosmic inflation, space expanded so rapidly that regions of the universe that were once in contact were pushed beyond each other's horizons, moving apart faster than light could travel between them. Even today, on scales larger than tens of billions of light-years, the expansion of space causes distant galaxies to recede from us faster than the speed of light. we will never be able to see or reach these galaxies, not because they're moving through space faster than light, but because the space between us is growing faster than light can traverse it. Fact 26. The universe has no edge and no center. This is deeply counterintuitive, but it's a consequence of expansion happening everywhere at once. If you could somehow travel in a straight line in any direction forever, you would never reach a boundary or edge. You wouldn't loop back to your starting point either, unless the universe has a specific kind of curved geometry, which current evidence suggests it doesn't. The universe appears to be flat, or very nearly flat, on the largest scales, extending infinitely in all directions. Every point in the universe sees itself as the center of the expansion, with all distant galaxies receding uniformly in every direction. There is no special place, no cosmic downtown, no privileged vantage point from which the universe looks fundamentally different. Fact 27. We can only observe a finite portion of the universe called the observable universe. Light travels at a finite speed, and the universe has existed for a finite time. So there's a maximum distance from which light could have reached us since the Big Bang. This distance defines the boundary of the observable universe, currently about 93 billion light-years in radius. Note that this is much larger than 13.8 billion light-years, the age of the universe in years, because the universe has been expanding while light travels toward us. Beyond this horizon, there is presumably more universe, potentially infinite in extent, but we cannot see it. Light from those regions hasn't had time to reach us yet. As time passes, our observable universe grows larger, encompassing previously unreachable regions. But because the expansion is accelerating due to dark energy, there are galaxies we can see now that we will never see again, carried beyond our future horizon by the relentless growth of space. Fact 28. The expansion rate varies at different cosmic epochs. In the earliest moments after the Big Bang, the universe expanded at an almost incomprehensible rate during inflation. After inflation ended, the expansion slowed dramatically, governed by the gravity of matter and radiation. For billions of years, the expansion continued to decelerate. The mutual gravitational attraction of everything in the universe acting as a brake. Then, about 5 billion years ago, something changed. The expansion began to accelerate again, as dark energy, which had always been present, but whose effect becomes more significant as matter spreads thinner, started to dominate. This accelerating expansion was entirely unexpected when it was discovered in 1998. It earned the Nobel Prize in Physics in 2011 and transformed our understanding of the universe's fate. Fact 29. Type Ia supernovae serve as standard candles for measuring cosmic expansion. These stellar explosions occur when a white dwarf in a binary system accumulates matter from its companion. and reaches a critical mass limit, triggering a runaway thermonuclear explosion. Because they all reach roughly the same mass before exploding, Type Ia supernovae have remarkably consistent peak brightness. Astronomers can use this consistency to determine distances. If you know how bright something actually is, and you measure how bright it appears, you can calculate how far away it must be. By observing Type Ia supernovae in distant galaxies, astronomers have mapped the expansion history of the universe, revealing that the expansion is accelerating. Recent studies suggest these standard candles may not be quite as standard as once thought, with the brightness of supernovae potentially affected by the age of their progenitor stars, adding new complexity to cosmic distance measurements. Fact 30. Redshift tells us how much the universe has expanded since light began its journey. When we observe light from distant galaxies, we find that it's stretched to longer, redder wavelengths. This redshift occurs because the universe expanded while the light was traveling toward us, stretching the light along with space itself. The amount of redshift directly indicates how much expansion occurred during the light's journey. A galaxy with a redshift of 1 means the universe has doubled in size since its light was emitted. A redshift of 3 means the universe has grown 4-fold. The most distant galaxies we've observed have redshifts greater than 10, meaning the universe has expanded more than 11-fold since their light began traveling. Redshift is a time machine, allowing us to see the universe as it was in the distant past, progressively younger and smaller the farther we look. Fact 31. The universe could be infinite in size. We know the observable universe is finite, bounded by the cosmic horizon beyond which light hasn't had time to reach us. But the total universe could extend far beyond what we can observe, potentially forever. If the universe is flat or has very slight negative curvature, as current measurements suggest, it could be infinite in spatial extent. This means there could be an infinite number of galaxies, an infinite amount of matter and energy, stretching endlessly in all directions. Alternatively, the universe could have a finite size with a more complex topology, like the surface of a higher dimensional sphere, finite but without edges or boundaries. Current observations cannot definitively distinguish between these possibilities. The universe beyond our cosmic horizon remains forever beyond reach, its true extent a profound mystery. Fact 32. Measuring the universe's expansion has revealed a persistent problem called the Hubble tension, which may point to new physics. Different methods of measuring the Hubble constant, the rate of expansion, give systematically different results. Local measurements using relatively nearby cosmic distance ladders yield a value around 73 kilometers per second per megaparsec. Measurements from the cosmic microwave background, looking at the universe when it was just 380,000 years old, give about 67 kilometers per second per megaparsec. This roughly 10% discrepancy is statistically significant and persists despite improvements in measurements. It suggests either that our measurement techniques have subtle flaws we haven't identified, or that the universe's expansion has evolved differently than our standard model predicts, possibly requiring new particles, new forces, or modifications to general relativity. Resolving this tension is one of the highest priorities in observational cosmology. Stars and their life cycles. Fact 33. Stars form from collapsing clouds of gas and dust. In the cold, dark regions of space, vast molecular clouds drift, composed mostly of hydrogen, with traces of helium and heavier elements. When something disturbs such a cloud, perhaps a shock wave from a nearby supernova or a collision with another cloud, parts of it can become denser. As a region contracts under its own gravity, it heats up, and the growing warmth creates internal pressure that resists further collapse. Eventually, if enough mass accumulates, the core temperature reaches about 15 million degrees, hot enough for nuclear fusion to begin. Hydrogen atoms smash together with such force that their nuclei overcome electromagnetic repulsion and fuse into helium, releasing tremendous energy. The outward pressure from this fusion balances gravity's inward pull, and the protostar becomes a stable, main-sequence star, beginning a lifetime that could last anywhere from millions to trillions of years, depending on its mass. Fact 34. The smallest stars, called red dwarfs, can burn for trillions of years. These dim, cool stars have masses less than about half that of our Sun, and they're by far the most common type of star in the universe. Red dwarfs burn their hydrogen fuel so slowly and efficiently that none of them, anywhere in the universe, have yet reached the end of their lives. The universe simply isn't old enough. These patient, long-lived stars will continue shining long after the Sun and all larger stars have died, potentially providing warmth to any surviving planets for times that dwarf the current age of the cosmos. Some red dwarfs may live for 10 trillion years, nearly 1,000 times longer than the universe has currently existed. They represent the universe's future, the last stars that will still shine when everything else has gone dark. Fact 35. Massive stars live fast and die young. Stars, more than 8 times the mass of the Sun, burn with incredible brightness, fusing hydrogen into helium at a furious rate. They race through their fuel supplies in just millions of years, a cosmological blink of an eye. As they exhaust the hydrogen in their cores, they begin fusing helium into carbon, then carbon into heavier elements, working their way up the periodic table through layers of nuclear burning like an onion. Oxygen, neon, magnesium, silicon, each forms and fuses in turn until finally iron appears at the core. Iron fusion requires more energy than it releases, so the chain of fusion reactions abruptly ends. Without outward pressure from fusion to support it, the iron core collapses catastrophically in less than a second, triggering a supernova explosion that tears the star apart and briefly outshines an entire galaxy. Fact 36. The Sun is a main sequence star about halfway through its life. Our Sun has been fusing hydrogen into helium in its core for roughly 4.6 billion years, and will continue doing so for another 5 billion years. During this main sequence phase, which comprises about 90% of a star's lifetime, the Sun remains relatively stable, its size, temperature, and luminosity changing only gradually. The balance between gravity trying to compress the star and the pressure from fusion pushing outward maintains a steady equilibrium. When the Sun eventually exhausts the hydrogen in its core, it will exit the main sequence and begin the dramatic transformations that mark a star's death throes. But for now, and for all of human history past and future, the Sun shines steadily, a middle-aged star in the prime of its life. Fact 37. When a star like the Sun dies, it becomes a planetary nebula, and then a white dwarf. After the Sun runs out of hydrogen in its core, fusion will stall, and the core will contract and heat up. This heating will ignite hydrogen fusion in a shell surrounding the core, and the energy released will cause the star's outer layers to expand dramatically. The Sun will become a red giant, swelling until it engulfs Mercury and Venus, and perhaps even Earth. Helium fusion will begin in the core, producing carbon and oxygen. But the Sun isn't massive enough to fuse these heavier elements. Eventually, the outer layers will drift away in expanding shells of glowing gas, creating a beautiful but brief planetary nebula. What remains is the hot, dense core, a white dwarf roughly the size of Earth, but containing about half the Sun's original mass, supported by electron degeneracy pressure and cooling slowly over billions of years. Fact 38. White dwarfs are the fate of most stars in the universe. Any star with a mass between about half that of the Sun and 8 times the Sun's mass will eventually become a white dwarf. These stellar remnants are extraordinarily dense, packing masses comparable to the Sun into volumes no larger than Earth. A teaspoon of white dwarf material would weigh several tons. They don't undergo fusion anymore. They simply radiate away their residual heat, gradually cooling and fading over immense timescales. Based on calculations, after trillions of years, they should cool completely, becoming black dwarfs, cold, dark spheres of crystallized carbon and oxygen. But the universe isn't old enough yet for any black dwarfs to exist, making them purely theoretical objects. Every white dwarf that has ever formed is still at least faintly glowing, a slowly cooling ember from a stellar fire that burned for billions of years. Fact 39. Neutron stars are the collapsed cores of massive stars. When a star more than about 8 solar masses explodes as a supernova, its core collapses so violently that protons and electrons are forced together, forming neutrons. The resulting neutron star is one of the most extreme objects in the universe. Typical neutron stars pack 1 to 2 times the Sun's mass into a sphere only about 20 kilometers across. Their density is almost incomprehensible. A sugar cube-sized piece of neutron star material would weigh as much as all of humanity combined. The surface gravity is so intense that the escape velocity is about half the speed of light. Some neutron stars, called pulsars, spin hundreds of times per second, their magnetic fields channeling radiation into beams that sweep across space like a cosmic lighthouse. Neutron stars are laboratories for physics under the most extreme conditions, where matter exists in states that cannot be reproduced anywhere else. Fact 40. Supernovae are among the most energetic events in the universe. When a massive star explodes, it releases more energy in a few seconds than the Sun will emit over its entire 10 billion year lifetime. The explosion is so powerful that it can briefly outshine an entire galaxy containing hundreds of billions of stars. The shockwave from a supernova races outward at tens of thousands of kilometers per second, heating and enriching the surrounding interstellar medium with heavy elements forged in the star's core and in the explosion itself. Without supernovae, there would be no carbon, oxygen, iron, or any of the other heavy elements essential for planets and life. Every atom heavier than helium in your body was created in a star and scattered into space by a supernova. You are quite literally made of stardust, the ashes of stellar fires that burned and died before the sun was born. Fact 41. Some of the largest stars are predicted to end their lives in pair instability supernovae, potentially leaving nothing behind. When a truly massive star, more than about 130 times the Sun's mass, reaches the end of its life, theoretical models suggest something even more extreme could occur. The core becomes so hot that gamma-ray photons begin converting into electron-positron pairs, a process that removes energy and causes the core to collapse even faster. The collapse could be so violent that the rebound explosion completely disrupts the star, leaving no remnant neutron star or black hole. The entire star would be blown to bits, scattered into space. These explosions, if they occur as predicted, may represent the maximum energy a single star can release. Pair instability supernovae may have been more common in the early universe when very massive population 3 stars formed, but they would be exceedingly rare in the modern cosmos, where metallicity makes it harder for such giants to exist. Though we haven't definitively observed one yet, astronomers are searching for their distinctive signatures. Fact 42. The heaviest elements are created in neutron star collisions. For decades, astronomers believed that supernovae created all heavy elements, but observations of kilonova explosions, caused when two neutron stars spiral together and merge, revealed that these violent events produce vast quantities of gold, platinum, uranium, and other elements heavier than iron. The extreme conditions during a neutron star merger, with temperatures exceeding billions of degrees and densities approaching that of atomic nuclei, provide the perfect environment for rapid neutron capture, a process that builds up the heaviest elements in the periodic table. A single neutron star collision can produce several Earth masses of gold alone. Every gold atom in every ring, every coin, every nugget ever found on Earth was likely forged in the cataclysmic merger of neutron stars billions of years ago, then scattered through space to eventually coalesce into our solar system. Fact 43. Stars come in a vast range of sizes, colors, and temperatures. The smallest main sequence stars, red dwarfs, are barely 1/10 the Sun's mass and about 1/100th as bright, glowing with a dim red light at surface temperatures around 3,000 degrees. The largest stars, hypergiants, can exceed 200 solar masses, shine with the light of millions of suns, and burn blue-white at temperatures above 30,000 degrees. Between these extremes lies every conceivable variation. Yellow stars, like our Sun. Orange stars, slightly cooler. Blue supergiants, burning fast and bright. These characteristics aren't random. They're determined almost entirely by one factor: the star's mass. More massive stars burn hotter, brighter, and faster. Less massive stars burn cooler, dimmer, and slower. The relationship between mass, temperature, color, and luminosity is so consistent that astronomers can determine a star's fundamental properties from its spectrum alone. Fact 44. The nearest star to the Sun, Proxima Centauri, is a red dwarf just over 4 light-years away. If you could travel at the speed of light, it would take more than 4 years to reach it. At the speed of current spacecraft, the journey would take tens of thousands of years. Proxima Centauri is much smaller and dimmer than the Sun, with only about 1/8 the Sun's mass and producing just 1/600th as much light. It's so faint that despite being our nearest stellar neighbor, it's invisible to the naked eye from Earth. Proxima Centauri has at least one planet, Proxima Centauri b, a rocky world in the star's habitable zone where liquid water might exist. This planet orbits incredibly close to its star, completing one orbit in just 11 days. But because Proxima Centauri is so cool and dim, the planet receives similar amounts of energy to what Earth receives from the Sun. It's one of the closest potentially habitable worlds we know of, though whether it's actually habitable is unclear, as red dwarfs often produce violent flares that could strip away a planet's atmosphere, black holes, and extreme physics. Fact 45. Black holes are regions of space-time where gravity is so strong that nothing can escape, not even light. When matter becomes compressed beyond a critical density, its gravity becomes so intense that it warps space-time to an extreme degree, creating a boundary called the event horizon. Once anything crosses this boundary, it can never return. The event horizon isn't a physical surface you could touch. It's simply the point of no return, the distance from which the escape velocity exceeds the speed of light. Because light cannot escape, black holes appear perfectly black against space, visible only by their effects on surrounding matter and light. Material falling toward a black hole typically forms an accretion disk, a swirling maelstrom of superheated gas and dust that glows brightly in X-rays before crossing the event horizon and disappearing forever. Fact 46. At the center of a black hole, general relativity predicts a singularity, a point where all the black hole's mass would be compressed to infinite density. However, physicists don't know whether this mathematical prediction reflects physical reality. The theory breaks down at that point, producing nonsensical infinities that suggest we're missing something fundamental. It's likely that a complete theory of quantum gravity, which we don't yet have, would describe the singularity differently, perhaps as a region of extremely high but finite density where the laws of physics take a form we don't yet understand. Inside the event horizon, space-time is so severely curved that all paths lead inward toward the singularity. Even light cannot travel outward. Time and space exchange roles in a sense, just as you inevitably move forward in time outside a black hole. Once inside the event horizon, you inevitably move inward toward whatever lies at the center. There's no force in the universe that could prevent it, based on our current understanding of physics. Fact 47. There are probably millions of black holes in the Milky Way galaxy alone. Most of these are stellar mass black holes, the remnants of massive stars that exploded as supernovae. These black holes typically have masses between about 3 and several dozen times the Sun's mass. They're extraordinarily difficult to detect because they emit no light and are tiny compared to stars, perhaps only tens of kilometers across. Astronomers find them primarily by observing their effects on nearby stars. If a black hole is part of a binary system, it can pull matter from its companion star. This material forms an accretion disk that heats up through friction and emits X-rays before spiraling into the black hole. By studying these X-ray binaries, astronomers have confirmed the existence of dozens of stellar mass black holes in our galaxy, but the total population is likely much larger, with millions of isolated black holes drifting unseen through space. Fact 48. Supermassive black holes lie at the centers of most galaxies. These monsters are completely different from stellar mass black holes, not just in size, but in origin. Supermassive black holes have masses ranging from millions to billions of times the Sun's mass. The one at the center of the Milky Way, Sagittarius A star, is about 4 million solar masses. The largest known supermassive black holes exceed 40 billion solar masses. How these giants formed remains uncertain. They're too massive to have formed from individual star collapses, and they existed when the universe was very young, less than a billion years after the Big Bang. Not nearly enough time for stellar mass black holes to grow through accretion. They may have formed from direct collapse of massive gas clouds in the early universe, or from mergers of smaller black holes, or through some process we haven't yet imagined. Understanding supermassive black hole formation is one of the outstanding problems in astrophysics. Fact 49. Black holes are not cosmic vacuum cleaners. This is one of the most common misconceptions. If you replace the Sun with a black hole of the same mass, Earth's orbit wouldn't change. We would continue orbiting just as we do now, though we'd freeze in the dark. Black holes only have extreme effects on material that comes very close to them. From a distance, their gravity is no different from that of any other object with the same mass. You'd have to get within a few Schwarzschild radii, the distance to the event horizon, before tidal effects and extreme gravity become significant. If you're safely outside this region, you can orbit a black hole indefinitely, just as you can orbit a star or planet. The danger comes from getting too close, where tidal forces stretch and compress anything unlucky enough to approach, a process called spaghettification. Fact 50. All black holes spin. When a star collapses to form a black hole, it conserves angular momentum, so any rotation the star had is concentrated into the much smaller black hole, causing it to spin extremely rapidly. The fastest known black hole, GRS 1915 plus 105, rotates more than 1,000 times per second. Black hole spin affects the surrounding space-time, dragging it along in a phenomenon called frame dragging. Near a rapidly spinning black hole, it becomes impossible to remain stationary. Space-time itself is rotating, carrying everything with it. The spin also affects the black hole's structure, determining the shape of its event horizon and the properties of the ergosphere, a region outside the event horizon where particles can still escape but cannot remain still. Black hole spin may be crucial for launching relativistic jets, narrow beams of particles and energy that some black holes emit at nearly the speed of light. Fact 51. Black holes could theoretically evaporate through Hawking radiation, though this has never been observed. In the 1970s, physicist Stephen Hawking showed that quantum effects near the event horizon should cause black holes to emit radiation and slowly lose mass. The mechanism involves virtual particle-antiparticle pairs that constantly appear and annihilate in empty space. Near a black hole's event horizon, one particle could fall in while the other escapes. To an outside observer, it would look like the black hole is emitting particles. Because the escaping particle carries away energy, the black hole should gradually lose mass. For stellar mass and supermassive black holes, this Hawking radiation would be utterly negligible, far colder than the cosmic microwave background. So they actually gain more mass from absorbing radiation than they would lose through evaporation. But in principle, after incomprehensible timescales, maybe 10 to the 100 years or more, black holes should completely evaporate according to Hawking's calculations. This creates another paradox, because information that falls into a black hole seems to be lost when it evaporates, potentially violating principles of quantum mechanics. Fact 52. Time behaves strangely near black holes. General relativity predicts that gravity slows time. The stronger the gravitational field, the slower time passes. Near a black hole's event horizon, time dilation becomes extreme. If you could watch an object fall toward a black hole from a safe distance, you would never see it cross the horizon. As it approached, it would appear to slow down. Its light redshifted and dimmed, asymptotically approaching but never quite reaching the event horizon. From the falling object's perspective, however, the crossing happens in finite time. There's no special moment, no barrier to break through. The event horizon passes unremarkably, though once crossed, escape becomes impossible. This difference in perspectives, where one observer sees the object frozen at the horizon forever, while another sees it fall through and reach the singularity, highlights the relative nature of time in extreme gravitational fields. Fact 53. The Event Horizon Telescope captured the first image of a black hole in 2019. By coordinating observations from radio telescopes around the world, effectively creating an Earth-sized telescope, astronomers imaged the shadow of the supermassive black hole at the center of the galaxy M87. The image showed a glowing ring of hot gas surrounding a dark central region, the black hole's shadow. This shadow appears larger than the event horizon itself because the black hole's gravity bends light from behind it, creating a dark silhouette. The achievement was a triumph of observation and computation, confirming predictions of general relativity and providing direct visual evidence of a black hole. In 2022, the collaboration released an image of Sagittarius A star, the supermassive black hole at the center of our own galaxy, offering a glimpse of the monster that lurks at the Milky Way's heart. Fact 54. Colliding black holes create gravitational waves. When two black holes orbit each other, they lose energy by emitting gravitational waves, ripples in space-time itself, that propagate outward at the speed of light. As they lose energy, the black holes spiral closer together, orbiting faster and faster until they merge in a cataclysmic collision. In the final fraction of a second, the black holes release more energy in gravitational waves than all the stars in the observable universe emit in light. These waves, predicted by Einstein's general relativity, were directly detected for the first time in 2015 by the LIGO Observatory. The discovery opened an entirely new window on the universe, allowing astronomers to observe events that produce no light, offering insights into black hole populations, testing general relativity in its most extreme regime, and providing an independent way to measure cosmic distances and the universe's expansion rate. Fact 55. The closest known black hole to Earth is Gaia BH1, about 1,500 light-years away. This is reassuringly distant. There are no black holes anywhere near close enough to pose any danger to our solar system. Gaia BH1 is a stellar mass black hole about 10 times the Sun's mass, orbiting a Sun-like star. It was discovered through careful observations of the star's motion. The star wobbles as it orbits an invisible companion, and detailed analysis revealed that companion must be a black hole. Most black holes are found in binary systems like this, where their gravitational influence on a visible companion betrays their presence. Isolated black holes drifting alone through space are nearly impossible to detect directly, though they occasionally reveal themselves through gravitational lensing when they pass in front of distant stars, temporarily brightening them through their gravitational focusing effect. Fact 56. The largest black holes ever discovered, ultramassive black holes, have masses exceeding tens of billions of times the Sun. The current record holder, TON 618, may have a mass around 66 billion solar masses. Though uncertainties in such measurements are large, these monsters lie at the centers of the most massive galaxies and quasars. Their event horizons are larger than our entire solar system. How they grew so massive remains unclear, requiring either extremely efficient accretion over billions of years or formation from already massive seeds in the early universe. They may represent an upper limit on black hole mass, as objects much larger would have difficulty forming within the current age of the universe. Even at their enormous size, they're still tiny compared to the galaxies they inhabit, typically containing only a fraction of a percent of the galaxy's total mass. Yet their gravitational influence shapes galaxy formation and evolution on the largest scales. Galaxies and cosmic structures. Fact 57. The universe contains hundreds of billions of galaxies, each containing hundreds of billions of stars. Every point of light you see in deep space telescope images is a galaxy, many of them containing more stars than you could count in 1,000 lifetimes. The sheer scale is almost impossible to grasp. Our Milky Way, a major galaxy by most standards, is just one among countless trillions of stars spread across the cosmos, and each of those stars could potentially have planets, moons, and perhaps life. The universe is not just large, it's incomprehensibly vast, filled with more worlds and possibilities than the human mind can truly contemplate. When you look at the night sky, you're seeing a tiny sample of this immensity, a few thousand nearby stars in our own galactic neighborhood, a fraction of what exists. Fact 58. Galaxies come in several basic types: spiral, elliptical, and irregular. Spiral galaxies, like the Milky Way and Andromeda, have flat, rotating disks of stars, gas, and dust organized into spiral arms with a central bulge of older stars. They're actively forming new stars in their spiral arms, where giant molecular clouds collapse to create stellar nurseries. Elliptical galaxies range from nearly spherical to elongated, football-shaped systems. They contain primarily old stars and little gas or dust, with little to no ongoing star formation. They likely form from galaxy mergers, where two spiral galaxies collide and their orderly structures are disrupted and mixed. Irregular galaxies have no clear structure, often appearing chaotic. Many are dwarf galaxies, small companions to larger systems, or galaxies disturbed by interactions with neighbors. Most galaxies don't fit neatly into categories, but show characteristics of multiple types, reflecting their complex formation and evolutionary histories. Fact 59. Galaxies are organized into groups and clusters. The Milky Way is part of the local group, a collection of more than 50 galaxies spanning about 10 million light-years. The two largest members are the Milky Way and Andromeda, each with their own families of satellite galaxies. Galaxy groups like ours are common, containing tens to hundreds of galaxies bound together by mutual gravity. Larger structures, called galaxy clusters, contain hundreds to thousands of galaxies and span tens of millions of light-years. The Virgo cluster, the nearest large cluster to us, contains more than 1,000 galaxies. Even clusters aren't the largest structures. They're organized into superclusters, enormous complexes of galaxy clusters and groups spanning hundreds of millions of light-years. Our local group belongs to the Laniakea supercluster, which contains about 100,000 galaxies. Fact 60. The Milky Way and Andromeda galaxies are on a collision course. They're approaching each other at about 110 kilometers per second, and in about 4 to 5 billion years, they will collide. Despite the violence implied by collision, individual stars almost certainly won't hit each other. Space between stars is so vast that most stars will pass by each other harmlessly, but the galaxy's shapes will be dramatically altered. Gravitational interactions will fling some stars into intergalactic space, while others plunge toward the merged galaxy's core. The collision will trigger intense bursts of star formation as gas clouds collide and compress. Supermassive black holes at each galaxy's center will spiral together and eventually merge, releasing tremendous gravitational waves. The final product, perhaps 5 billion years after the collision begins, will be a giant elliptical galaxy, sometimes called Milkomeda, a blend of both galaxies' stars in a new, more symmetric configuration. Fact 61. The first galaxies formed surprisingly early in the universe's history. Observations from the James Webb Space Telescope have detected galaxies that existed just a few 100 million years after the Big Bang, less than 2% of the universe's current age. These ancient galaxies challenge our understanding of how structures form. Standard models of galaxy formation suggested that galaxies should grow gradually, starting small and growing over billions of years through mergers and accretion. But some of these early galaxies appear surprisingly mature, already containing billions of stars and massive black holes. How they formed so quickly remains a puzzle. It may require revising models of early star formation or invoking unusual conditions in the early universe that don't exist today. These discoveries highlight how much we still have to learn about cosmic history. Fact 62. Most galaxies have supermassive black holes at their centers. The relationship between galaxies and their central black holes is one of the most intriguing in astrophysics. The black hole's mass is tightly correlated with properties of the galaxy's central bulge, suggesting they grow together through some shared process. When galaxies merge, their central black holes sink to the center of the merged system and eventually coalesce. The process of accretion onto supermassive black holes can release enormous energy, often expelled in jets of particles moving at nearly light speed. These jets can extend millions of light years beyond the galaxy, heating intergalactic gas and affecting star formation. In some galaxies, the central black hole is actively feeding, creating brilliant quasars or active galactic nuclei. In others, including the Milky Way, the central black hole is relatively quiescent, consuming little material and producing minimal luminosity. Fact 63. Quasars are the most luminous, persistent objects in the universe. These are supermassive black holes actively accreting matter at enormous rates, releasing so much energy that they can outshine their entire host galaxies. The brightest quasars emit more than 1,000 times the light of the entire Milky Way from a region no larger than our solar system. Material in the accretion disk around the black hole heats to millions of degrees, radiating across the electromagnetic spectrum from radio waves to X-rays. Quasars were more common in the early universe when galaxies had abundant gas supplies to feed their central black holes. Most nearby large galaxies likely went through quasar phases billions of years ago when they were younger and more active. Today's quasars are rare, their fuel supplies mostly exhausted, their light reaching us from billions of light years away, showing us what galaxies looked like when the universe was young. Fact 64. Dwarf galaxies are the most common type of galaxy in the universe. These small galaxies, containing anywhere from a few million to a few billion stars, vastly outnumber giant galaxies like the Milky Way. Many orbit larger galaxies as satellites. The Milky Way has dozens of known dwarf galaxy companions, and there are probably many more too faint to detect. Some dwarf galaxies contain almost no dark matter, a puzzling observation that challenges galaxy formation models. Others, called ultra-faint dwarfs, contain more dark matter than ordinary matter by huge margins, making them among the darkest objects in the universe. Dwarf galaxies are important for understanding galaxy formation because they're the building blocks from which larger galaxies are assembled. Most of the stars in giant galaxies may have originally formed in smaller galaxies that were later accreted. Fact 65. The cosmic web is the largest scale structure in the universe. On scales of hundreds of millions of light-years, the universe organizes itself into an intricate network of filaments and walls separated by vast voids. Galaxies cluster along the filaments like beads on strings, drawn there by the gravitational attraction of underlying dark matter. Where filaments intersect, massive galaxy clusters form, the nodes of the cosmic web. The voids between filaments contain far fewer galaxies, creating an almost empty space that can span hundreds of millions of light-years. This web-like pattern emerged from tiny density fluctuations in the early universe. Regions that were slightly denser attracted more matter through gravity, growing denser still, while less dense regions lost matter to their surroundings. Over billions of years, this process amplified small differences into the magnificent large-scale structure we observe today. Fact 66. Galaxies come in a vast range of sizes. The smallest dwarf galaxies contain only a few thousand stars and span just a few hundred light-years. The largest galaxies, giant ellipticals at the centers of galaxy clusters, can contain hundreds of trillions of stars and span millions of light-years. The Milky Way, with its roughly 200 billion stars and a diameter of about 100,000 light-years, is a fairly large galaxy, but far from the biggest. IC 101, one of the largest known galaxies, is about 60 times wider than the Milky Way and may contain 100 trillion stars. The size differences are staggering, with the largest galaxies containing millions of times more stars than the smallest. Most galaxies fall somewhere in the middle range, but the extremes are remarkable, highlighting the diversity of structures the universe produces. Fact 67. Galaxies evolve and change over cosmic time. The galaxies we see today look different from galaxies in the early universe. Young galaxies tend to be smaller, bluer, more irregular, and more actively forming stars. Over billions of years, they grow through mergers and accretion. Their star formation gradually declines as they consume or expel their gas supplies, and they settle into more regular shapes. Many spiral galaxies in the modern universe will eventually become elliptical galaxies after experiencing major mergers. Galaxy evolution is not a simple linear process. It depends on environment, with galaxies in dense clusters evolving differently from those in relative isolation. By studying galaxies at different distances and therefore different cosmic times, astronomers can piece together how galaxy populations change and understand the physical processes driving that evolution. Fact 68. The observable universe is estimated to contain about 2 trillion galaxies. This number comes from deep field observations by space telescopes like Hubble and James Webb, which have peered into tiny patches of sky to count the number of galaxies at various distances and brightness levels, then extrapolated to the full sky. The actual number could be higher or lower, with significant uncertainties, especially for the faintest, most distant galaxies that are hardest to detect. 2 trillion is a staggering number, more galaxies than there are stars in the Milky Way. And remember, this is just the observable universe, the portion we can in principle see. The total universe, if it extends beyond our cosmic horizon, could contain infinitely more. Every single one of those 2 trillion galaxies is a vast collection of stars with its own history, structure, and characteristics. The diversity and abundance of galaxies remind us how vast and varied the universe truly is. Light, radiation, and cosmic signals. Fact 69. Light travels at approximately 300,000 kilometers per second in a vacuum. This is the cosmic speed limit, the fastest anything can possibly travel. Nothing with mass can reach light speed, and even light itself is subject to this limit. The speed of light isn't just a speed, it's a fundamental constant that defines the relationship between space and time. Its value determines how events in space and time are connected, forming the foundation of special relativity. When we look at distant objects, we're seeing them as they were in the past, because light takes time to travel. The farther away something is, the older the light is that reaches us. Light from the sun is about 8 minutes old when it reaches Earth. Light from the nearest star is over 4 years old. Light from distant galaxies can be billions of years old, offering a window into the universe's distant past. Fact 70. The electromagnetic spectrum extends far beyond visible light. Visible light, the rainbow of colors our eyes can see, comprises only a tiny sliver of the full electromagnetic spectrum. At longer wavelengths are radio waves, microwaves, and infrared radiation. At shorter wavelengths are ultraviolet, X-rays, and gamma rays. All of these are fundamentally the same phenomenon. Oscillating electric and magnetic fields traveling through space, differing only in wavelength and energy. Astronomers observe the universe across the entire spectrum because different processes emit at different wavelengths. Cool gas clouds glow in radio waves. Stars emit primarily in visible and ultraviolet. Extremely hot gas around black holes radiates X-rays. By observing in multiple wavelengths, astronomers build a complete picture of cosmic phenomena that would be invisible in any single band. Fact 71. The cosmic microwave background is the oldest light in the universe. Emitted when the universe was just 380,000 years old, this radiation has been traveling through space for over 13 billion years. Originally emitted as visible and ultraviolet light from the hot plasma of the early universe, it has been stretched by cosmic expansion to microwave wavelengths, with a temperature today of just 2.7 degrees above absolute zero. The cosmic microwave background is remarkably uniform, looking almost the same in every direction, but tiny temperature variations of about 1 part in 100,000 have been precisely mapped. These variations, imprinted when the universe was young, represent the seeds of all structure. Slightly warmer regions were slightly denser, eventually collapsing to form galaxies and clusters. The cosmic microwave background is one of the most important discoveries in cosmology, providing a direct observation of the early universe and confirming many predictions of Big Bang theory. Fact 72. Gravitational waves are ripples in space-time itself. First predicted by Einstein's general relativity, these waves are produced by accelerating massive objects, particularly in catastrophic events like colliding black holes or neutron stars. Unlike electromagnetic waves, which are oscillations in electric and magnetic fields, gravitational waves are actual deformations of space and time, stretching and compressing distances as they pass. They travel at the speed of light and can pass through matter almost unimpeded, carrying information from events that produce no light at all. The detection of gravitational waves in 2015 opened an entirely new way of observing the universe. Gravitational wave astronomy allows us to study phenomena invisible to conventional telescopes, test general relativity in its most extreme regime, and observe the universe's most violent events in exquisite detail. Fact 73. Nearly all of the light in the universe comes from stars. Whether directly from the surface of stars or indirectly through processes powered by stars, stellar radiation dominates the cosmic energy budget of electromagnetic radiation. Active galactic nuclei, powered by supermassive black holes, can briefly outshine entire galaxies, and quasars can be among the brightest objects in the universe, but averaged over cosmic history. Stars are the primary light sources. Our Sun, an ordinary middle-aged star, produces more energy in 1 second than all of human civilization has produced throughout history. Multiply that by hundreds of billions of stars in each of 2 trillion galaxies, and you begin to appreciate the staggering total luminosity of the universe. Yet even this is dwarfed by the energy in dark matter and dark energy, which don't emit light at all. Fact 74. We can see objects whose light has taken longer than the age of the universe to reach us. This sounds paradoxical, but makes sense when you account for cosmic expansion. The most distant observable galaxies are currently about 46 billion light-years away. Their light has been traveling toward us for over 13 billion years, nearly the full age of the universe. But during that time, the universe has been expanding. So those galaxies are now much farther away than when they emitted the light we're seeing. The observable universe, the region from which light has had time to reach us, is not a sphere 13.8 billion light-years in radius. It's a sphere about 93 billion light-years in diameter. The expansion of space stretches not just the wavelength of light, but also the effective distance light has traveled, allowing us to see objects that are now much farther away than their light travel time would suggest. Fact 75. Neutrinos from the Sun pass through your body constantly. Every second, trillions of neutrinos produced by nuclear fusion in the Sun's core stream through your body, through the Earth, and out the other side without interacting. Neutrinos are ghostly particles with almost no mass and no electric charge. They interact with matter only through the weak nuclear force and gravity, both extraordinarily feeble compared to electromagnetic forces. As a result, neutrinos can pass through enormous amounts of material without being absorbed or deflected. Detecting them requires huge, ultra-sensitive detectors, often placed deep underground to shield against other particles. Neutrino astronomy offers a unique window into stellar interiors and violent cosmic events. The only neutrinos ever detected from beyond the solar system came from supernova 1987A, an explosion in a nearby galaxy, providing crucial confirmation of supernova models. Fact 76. Cosmic rays are high-energy particles, mostly protons, that constantly bombard Earth from space. Despite their name, they are not rays but particles, accelerated to enormous energies by supernova shockwaves, pulsars, and other violent cosmic processes. Some cosmic rays have energies millions of times greater than particles in our most powerful accelerators, carrying as much energy as a thrown baseball packed into a single atomic nucleus. When these particles strike Earth's atmosphere, they create cascades of secondary particles that shower down to the surface. Cosmic rays were actually the first source of high-energy particles discovered and played a crucial role in early particle physics research. They also present a hazard for astronauts and spacecraft electronics, as they can damage DNA and disrupt sensitive equipment. Understanding cosmic rays helps us study both particle physics and the violent processes that produce them throughout the universe. Fact 77. The universe is filled with photons from the cosmic microwave background, about 400 photons per cubic centimeter on average. This may not sound like much, but it's far more than the average density of atoms, which is less than 1 per cubic meter in intergalactic space. The universe contains many more photons than baryons, particles like protons and neutrons. Most of these photons are low-energy microwave radiation, individually carrying very little energy, but their sheer numbers make them significant. There are roughly 10 billion cosmic microwave background photons for every atom in the universe. This radiation field fills all of space uniformly, creating a gentle bath of microwave light that permeates the cosmos, a cool remnant of the universe's hot youth. Fact 78. The faintest objects we can detect with the most powerful telescopes are billions of times fainter than the dimmest stars visible to the naked eye. The human eye can see stars down to about sixth magnitude, a measure of brightness. The Hubble Space Telescope can detect objects as faint as 31st magnitude, roughly 4 billion times fainter. The James Webb Space Telescope, with its larger mirror and sensitivity to infrared light, can detect even fainter and more distant objects. These incredibly faint signals require long exposures, sometimes hours or even days, to accumulate enough photons to form an image. The deep field images produced by these telescopes, showing thousands of galaxies in tiny patches of sky, represent some of the deepest views into space and time ever achieved. Each faint smudge of light is a galaxy billions of light years away, its light stretched and dimmed by expansion, carrying information about cosmic conditions billions of years in the past. The building blocks of everything. Fact 79. Atoms are mostly empty space. If you could magnify an atom to the size of a sports stadium, the nucleus would be like a tiny pea at the center, and the electrons would be orbiting somewhere out near the walls. The vast majority of the atom's volume contains nothing but empty space. And yet atoms feel solid when they interact, held apart by electromagnetic forces between their electron clouds. The repulsion you feel when you touch something isn't atoms physically bumping together like billiard balls. It's the electromagnetic force between electrons in your hand and electrons in the object pushing against each other. At the quantum level, matter is mostly emptiness, held together by forces. Fact 80. Only 3 stable elements lighter than iron were created in the Big Bang. Hydrogen, helium, and lithium formed in the first few minutes of the universe's existence through Big Bang nucleosynthesis. All heavier elements, from carbon to uranium, were forged in stars or in stellar explosions. Inside stars, nuclear fusion builds up heavier elements step by step. Hydrogen fuses to helium. Helium fuses to carbon and oxygen. In massive stars, the process continues through neon, magnesium, silicon, and finally iron. But iron fusion requires more energy than it releases, so the chain stops there. Elements heavier than iron are primarily created in supernova explosions and neutron star collisions, where the extreme conditions allow rapid neutron capture to build up the heaviest nuclei. Every carbon atom in your body, every oxygen atom you breathe, every calcium atom in your bones was created inside stars and scattered into space by stellar death. You are made from processed stellar material. Fact 81. The universe is about 75% hydrogen and 25% helium by mass. This ratio has remained remarkably constant since shortly after the Big Bang, when these elements were synthesized. All the heavier elements combined, despite their importance for planets and life, constitute less than 2% of the universe's ordinary matter by mass. Even though stars have been converting hydrogen to helium and heavier elements for billions of years, and supernovae have been enriching space with heavy elements, the overall composition of the universe has changed very little. Most of the universe's gas remains in primordial form, never having been processed through stars. The hydrogen and helium that fills intergalactic space is nearly identical to the material that existed when the first stars formed. Fact 82. Complex molecules can exist in space. For many years, scientists thought interstellar space was too cold and harsh for complex chemistry. But observations, particularly from radio telescopes detecting molecular emission lines, have revealed a rich tapestry of molecules in space. More than 200 different molecules have been identified in interstellar clouds, some with more than 10 atoms. These include simple molecules like water, carbon monoxide, and ammonia, but also more complex organic molecules like alcohols, aldehydes, and even amino acids, the building blocks of proteins. These molecules form on the surfaces of dust grains where atoms can meet and bond, or in gas phase reactions in dense, shielded clouds. The presence of complex organic molecules in space raises intriguing questions about the origins of life. Did some of life's precursor molecules arrive on early Earth from space, delivered by comets and asteroids? Fact 83. The most common molecule in the universe is molecular hydrogen, while atomic hydrogen is the most abundant element. In cold, dense regions of space, hydrogen atoms pair up to form H2 molecular hydrogen. Giant molecular clouds, the largest structures in galaxies, contain vast quantities of molecular hydrogen, providing the raw material for star formation. These clouds can have masses millions of times that of the Sun and span hundreds of light years. Molecular hydrogen is difficult to detect directly because it has no permanent electric dipole moment and emits very weakly at the low temperatures typical of molecular clouds. Astronomers often use trace molecules like carbon monoxide as proxies to map the distribution of molecular hydrogen. These clouds are the nurseries where stars are born, their cold, dense cores collapsing under gravity to ignite nuclear fusion and create new stellar systems. Fact 84. Metals in astronomy aren't the same as metals in chemistry. Astronomers use the term metals to refer to any element heavier than helium. So carbon, oxygen, nitrogen, and even noble gases like neon are all metals in astronomical parlance. This unusual usage stems from the fact that hydrogen and helium were created in the Big Bang, while everything heavier was produced in stars. The metallicity of a star, gas cloud, or galaxy indicates how much stellar processing has occurred. The first stars, formed from primordial gas, had virtually zero metallicity. Modern stars and gas clouds have been enriched by many generations of stellar nucleosynthesis and explosions, giving them higher metallicity. By measuring metallicity, astronomers can determine the age and evolutionary state of stellar populations. Fact 85. Antimatter exists, but the universe is almost entirely made of matter. Every fundamental particle has an antimatter counterpart, with the same mass but opposite charge. When matter and antimatter meet, they annihilate in a burst of energy. According to the laws of particle physics as we understand them, the Big Bang should have created equal amounts of matter and antimatter. These should have annihilated each other, leaving a universe filled with photons, but no matter at all. Obviously, that didn't happen. For some reason, there was a tiny asymmetry, perhaps one extra matter particle for every billion matter-antimatter pairs. This small excess survived annihilation and became everything we see today. Why this asymmetry existed is one of the great unsolved mysteries in physics. Without it, atoms, stars, galaxies, planets, and life could not exist. The universe would be nothing but an expanding sea of radiation. Fact 86. The atoms in your body are ancient. Most of them are older than the Sun, older than Earth, billions of years old. The hydrogen atoms in your body, mostly in water molecules, formed in the first few minutes after the Big Bang, making them 13.8 billion years old. The carbon, nitrogen, oxygen, and other heavy elements were forged in stars that lived and died before our solar system formed. These atoms cycled through multiple generations of stars, were scattered into space by supernovae, drifted through interstellar clouds, and eventually coalesced into the nebula from which the Sun and Earth formed 4.6 billion years ago. From there, they became part of the raw materials that built our planet and eventually found their way into living organisms. You are assembled from debris that has witnessed nearly the entire history of the universe. Fact 87. The elements in the human body come from multiple cosmic sources. Hydrogen, the most abundant element in our bodies, is primordial, created in the Big Bang. Carbon, nitrogen, and oxygen, which together make up most of the remaining mass of living tissue, were synthesized in the cores of massive stars and dispersed by supernova explosions. Calcium in our bones and iron in our blood were also primarily made in supernovae. But heavier elements like iodine, essential for hormone production, may have been created in neutron star collisions. We are, quite literally, made of star stuff, but not just one kind of star stuff. We're assembled from atoms, that came from different cosmic processes, spread across space and time, eventually gathering on Earth and combining into the intricate structures of life. Fact 88. The concept of matter itself breaks down at quantum scales. At the deepest level, particles aren't tiny solid objects. They're quantum fields, excitations in underlying fields that permeate all of space. An electron isn't a little sphere orbiting the nucleus. It's a ripple in the electron field, exhibiting both particle-like and wave-like properties depending on how it's observed. The distinction between matter and energy blurs at these scales. Energy can convert to matter, and matter can convert back to energy, famously described by Einstein's E=mc squared. The seemingly solid, tangible world of everyday experience emerges from an underlying reality that's fundamentally strange, probabilistic, and far removed from our intuitive understanding. The building blocks of everything are themselves built from something even more fundamental and mysterious: time, space, and reality. Fact 89. Time and space are not separate, but intertwined into a four-dimensional fabric called space-time. Einstein's special relativity revealed that time is not absolute and universal. It's relative, flowing at different rates depending on motion and gravity. Two observers moving at different speeds will measure time passing at different rates, and neither is wrong. They're simply observing different projections of the same underlying space-time reality. General relativity extended this, showing that gravity isn't a force pulling on objects, but rather a curvature of space-time itself. Massive objects warp the fabric of space-time around them, and other objects follow the curves of that fabric. We perceive this as gravitational attraction, but it's actually objects following the straightest possible paths through curved space-time. Time and space can no more be separated than up and down or left and right. Fact 90. Looking deep into space is looking back in time. The finite speed of light means that when you observe distant objects, you're seeing them as they were when their light began its journey. The sun you see is 8 minutes in the past. The Andromeda galaxy appears as it was 2.5 million years ago. The most distant galaxies we observe appear as they were more than 13 billion years ago, when the universe was still in its infancy. Astronomers use this light travel time to map cosmic history. By observing objects at different distances, they're seeing snapshots from different epochs, allowing them to trace how galaxies, stars, and structure have evolved over billions of years. In a very real sense, telescopes are time machines, and the deeper we look into space, the farther back in time we see. Fact 91. Some theoretical frameworks suggest there may be other universes beyond our own. The concept of a multiverse, once relegated to science fiction, has become a serious topic of discussion among cosmologists and physicists, though it remains highly speculative. Some interpretations of cosmic inflation suggest that inflating regions of space could spawn new universes, each with potentially different physical constants and laws. String theory, attempting to unify quantum mechanics and gravity, predicts a vast landscape of possible vacuum states, each corresponding to a universe with different properties. The many worlds interpretation of quantum mechanics proposes that every quantum measurement splits reality into multiple branches, each representing a different outcome. While these ideas arise naturally from attempts to understand fundamental physics, they currently lie beyond our ability to test or observe. If multiverses exist, our universe would be just one bubble in a vast, possibly infinite, cosmic foam. But this remains a theoretical possibility rather than established fact. Fact 92. The laws of physics appear to be the same everywhere in the observable universe. Spectroscopic observations of distant galaxies show the same atomic emission and absorption lines we see in laboratories on Earth. Stars in galaxies billions of light years away fuse hydrogen into helium through the same nuclear reactions as our Sun. The speed of light, the strength of gravity, the masses and charges of fundamental particles all appear constant across space and time. This uniformity is remarkable and not obviously necessary. We could imagine a universe where the laws of physics changed from place to place or evolved over time. The fact that they don't, as far as we can tell, makes the universe comprehensible and predictable. It's what allows us to use observations of distant objects to infer cosmic history and structure. Fact 93. Beyond the observable universe, there could be much more, possibly infinitely more, though this remains unknown. The observable universe is limited by the cosmic horizon. The distance light could have traveled since the Big Bang, but the total universe, if it extends beyond this horizon, could be vastly larger, perhaps even infinite. Cosmic inflation theory suggests that the full universe is exponentially larger than the observable portion. If inflation occurred as theorized, the universe expanded by at least a factor of 10 to the 26, creating a region far larger than we can observe. Beyond our horizon could lie countless other galaxies, stars, and structures, forever invisible to us because their light will never have time to reach us. If the universe is truly infinite, there's even a bizarre mathematical consequence. In an infinite universe with infinite possibilities, every possible arrangement of matter would eventually occur somewhere, though unfathomably far away. However, we may never be able to confirm whether the universe is finite or infinite, since by definition, we can only observe what lies within our cosmic horizon. Fact 94. We live in a golden age for observing the universe. We're fortunate to exist when the universe is transparent to most wavelengths of light. when stars and galaxies are abundant, and when the cosmic microwave background is still visible but cooled enough to allow detailed study. In the very early universe, conditions were too hot and dense for complex structures to exist. In the far future, as dark energy drives accelerating expansion, distant galaxies will be carried beyond our cosmic horizon, disappearing from view. Stars will eventually exhaust their fuel, and the universe will grow dark. Future civilizations, if any exist, will look out on an increasingly empty cosmos, with no evidence of other galaxies, no cosmic microwave background, nothing to suggest the universe had a beginning or contains anything beyond their local galaxy. They might conclude they inhabit a small, static, unchanging universe. We live when the universe is old enough to have interesting structures, but young enough that evidence of its history is still accessible. It's a privileged perspective, a window that will eventually close. Fact 95. The universe has no obligation to make sense to human minds. Our brains evolved to understand the African savanna, to track predators and find food, not to comprehend quantum mechanics or cosmic expansion. It's remarkable that we can understand the universe at all, that the mathematics and logic we've developed allow us to model and predict cosmic phenomena far removed from everyday experience. But there may be aspects of reality that are simply beyond our capacity to grasp, concepts so alien to human cognition that we can't even formulate the right questions. The universe existed for 13.8 billion years before humans appeared, and will continue for incomprehensible time after we're gone. It doesn't care whether we understand it, yet somehow, through observation, reason, and creativity, we've managed to glimpse its workings, to uncover laws and patterns that govern everything from the smallest particles to the largest structures. That we can understand anything at all is perhaps the greatest mystery. Fact 96. Some physicists propose that information may be the most fundamental concept in the universe, though this remains a matter of ongoing research and debate. At the quantum level, physics increasingly appears to be about information. Quantum states are destroyed by measurement. Quantum entanglement allows correlations that seem to transcend space. Black holes create paradoxes about whether information is preserved or destroyed. Some physicists argue that space-time itself might emerge from quantum information, that reality at its deepest level could be computational rather than material. Based on this perspective, the universe might be better understood as a vast quantum computer, processing information according to physical laws, with matter and energy as manifestations of that computation. This view, still highly speculative and far from established, suggests that the ultimate nature of reality might not be particles or fields, but information itself, patterns of possibility that crystallize into the physical world we observe. If this interpretation proves correct, it would represent a profound shift in how we conceptualize existence. The fate of the universe. Fact 97. The universe's ultimate fate depends on dark energy. If dark energy remains constant, as most evidence suggests, the universe will continue expanding forever, accelerating without bound. Galaxies will be carried apart by the expansion of space. Within 100 billion years, all but the nearest galaxies will be pushed beyond our cosmic horizon, invisible to any observers. Star formation will gradually cease as gas is used up or dispersed. Existing stars will burn out. In perhaps 10 trillion years, the last star will fade, and the universe will enter a dark age. After unimaginable timescales, even black holes will evaporate through Hawking radiation. The ultimate state would be a cold, dark, and dilute expanse approaching absolute zero, with any remaining particles separated by vast distances. A slow heat death where entropy reaches its maximum and nothing interesting can ever happen again. This scenario is called the Big Freeze, and current evidence suggests it's the most likely future. Fact 98. If dark energy is not constant, the universe's fate could be very different from current predictions. Recent preliminary observations hinting that dark energy might be weakening raise the possibility of alternative futures, though these remain speculative. If dark energy were to decay away, the universe's expansion could eventually halt and reverse, leading to a big crunch where space contracts, galaxies collide, and everything collapses back to a singularity, perhaps to be reborn in another Big Bang. Alternatively, if dark energy were to strengthen over time, it could lead to a big rip where expansion accelerates so violently that it overcomes gravity, then molecular bonds, then even nuclear forces, tearing apart galaxies, stars, planets, atoms, and finally subatomic particles themselves in a catastrophic end where the fabric of space-time is literally torn apart. Each scenario would lead to the destruction of all complex structures, but through very different mechanisms. The universe's fate remains profoundly uncertain, dependent on the nature of dark energy, which we still don't fully understand. Fact 99. In any scenario, the universe as we know it has a finite lifetime. Whether through heat death, collapse, or tearing, the structures that make the universe interesting, stars, galaxies, planets, life, will not last forever. On timescales of trillions of years, star formation will cease. On timescales of googles of years, black holes will evaporate. The universe's evolution from a hot, dense state to its eventual endpoint, whatever that may be, is a one-way journey. Entropy increases. Complexity emerges, but is temporary. We exist in a brief window when the universe supports structures capable of observing and understanding. Before us was a simpler time of gas and plasma. after us will come an era of increasing simplicity and emptiness. The universe had a beginning, and it will have an end, or at least an end to anything we would recognize as meaningful existence. This knowledge should not diminish, but rather enhance our appreciation for the present moment, for the extraordinary fact that we exist at all in this brief interval of cosmic fertility. Fact 100. The universe is simultaneously knowable and mysterious. We've learned an astonishing amount about the cosmos. We know its age to within a fraction of a percent. We've mapped its structure across billions of light years. We understand how stars work, how galaxies form, how elements are created. We've detected gravitational waves, imaged black holes, and traced cosmic history back to moments after the Big Bang. And yet, the more we learn, the more we discover we don't know. Dark matter and dark energy, which together constitute 95% of the universe, remain mysterious. We don't know if the universe is finite or infinite. We don't fully understand how structure formed so quickly after the Big Bang, or how supermassive black holes grew so rapidly. We don't know the universe's ultimate fate with certainty. We don't know if other universes exist, or whether the laws of physics could have been different. Perhaps most fundamentally, we don't know why the universe exists at all, or why it has the particular properties that allow for complexity, life, and consciousness. These mysteries are not failures of science, but invitations to continue exploring, to keep asking questions, to never stop wondering about this strange and beautiful cosmos we inhabit. And there you have it, 100 facts about the universe, from the Big Bang to black holes, from dark matter to the fate of everything. Each fact a glimpse into the vast cosmic story, a story that includes you, me, Earth, the Sun, our galaxy, and trillions more across space and time. The universe is old beyond imagining, yet still young in its existence. It's vast beyond comprehension, yet governed by elegant mathematical laws we can understand. It's mostly dark, mostly empty, yet filled with wonders, from newborn stars to colliding galaxies to the mysterious forces that shape it all. As you drift off tonight, remember that you're made of atoms forged in ancient stars. You're standing on a planet orbiting a sun in a galaxy that's part of a vast cosmic web stretching across billions of light years. You exist in this moment, this particular slice of space-time, part of a universe that began nearly 14 billion years ago and will continue evolving for time spans that dwarf all of human history. You are both infinitesimally small and profoundly connected to everything, a temporary pattern of matter and energy that has somehow become conscious, capable of contemplating the very cosmos that created you. The universe doesn't need us to exist. It doesn't require our understanding or appreciation. It simply is, unfolding according to physical laws, indifferent and impersonal. And yet, Here we are, conscious beings able to look out at the stars, measure their distances, analyze their light, reconstruct cosmic history, and marvel at the beauty and complexity of it all. That capacity for wonder, that ability to understand our place in the cosmos, is perhaps the universe's greatest achievement, the moment when it became aware of itself through us. So rest easy, knowing that you're part of something vast and ancient and ongoing. The universe spins on, galaxies drift through space, stars burn and die and are born again. And somewhere in the middle of it all, on a small blue planet, you exist for your brief moment, connected to everything through the atoms in your body and the light reaching your eyes from distant stars. If you've enjoyed this journey through the cosmos, if these facts have sparked your curiosity or helped you wind down after a long day, consider supporting the channel by liking this video and subscribing. There are so many more cosmic mysteries to explore, so many more facts to discover, and I'd love to share them with you. Until next time, sleep well and dream of stars. Good night.